Let's turn our attention now to how much energy is associated with translations. We can model translational energy with our particle in a box problem. We're going to put our particle in a large box, like a 10 milliliter beaker. Recall that the energy associated with a particle in a box is quantized with the quantum number n and depends inversely on the size of the box. In this case, because we have a three-dimensional box, we'll be needing the volume rather than the length of the box. Because we have three dimensions, the quantum number n is actually made up of three different quantum numbers, one for each direction. So n squared is the quantum number in the x direction squared plus the quantum number in the y direction squared plus the quantum number in the z direction squared. If we look at the set of discrete energy levels associated with the particle in a box, we notice that there are many, many levels, and many of them are degenerate. This arises because there are many ways to make a particular value of n using different values of nx, ny, and nz. So for instance, the lowest energy level has all quantum numbers nx, ny, and nz at their lowest level, which is equal to 1. The next higher energy level would have one of those quantum numbers in the next possible quantum state, which is 2. So for instance, nx could equal 2, while ny and nz both equal 1. However, I could also have ny equal to 2 with nx and nz equal to 1, or nz equal to 2 with nx and ny equal to 1. All of these states give the same value of n squared equal to 6. Therefore, these states are all degenerate, and the second level is threefold degenerate. The difference between any two adjacent energy levels is going to decrease as the mass increases or the size of my container increases. For a microscopic particle with masses in the range of 10 to the minus 26 kilograms, h squared over 8m is going to be much, 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 much smaller than the volume of a macroscopic container like a beaker. Therefore, delta E is going to be incredibly small. When we have very small differences between energy levels, our energy level diagram essentially looks like a continuous set of energies. This is simply the classical limit in which the particle can take on any energy it wants. And so we go to the classical limit as the size of our particle gets large and as the size of our container gets large.